Hey everyone, welcome to this explainer. If you've ever dealt with the absolute headache of securing microservices and thought to yourself, there just has to be a better way to handle authorization before routing even happens, well, you are definitely in the right place. Today, we're taking a really deep dive into a truly fascinating hackathon prototype designed specifically for modern zero trust environments. It's called Name-Based Secure Routing, or NBSR. We're going to unpack its security model, look at its exact request pipeline, and review the validated results that prove this thing actually works. Okay, let's dive right in. Here's our roadmap for today. First, we'll look at the limits of DNS, then move into the identity-aware NBSR architecture. After that, we'll break down the anatomy of routing tickets, explore back-end isolation, check out the validated results, and finally touch on the collaborative AI and human build process. All right, Section 1, the limits of DNS, location versus workload authorization. So think about standard network routing for a second. Traditional DNS is absolutely brilliant at answering one simple question. Where is this service located, right? It resolves a name to an IP address and boom, you're routed. But here's the thing. In a zero trust world, that is just not going to cut it anymore because DNS has absolutely zero concept of workload authorization. It's kind of like a GPS. It tells you exactly how to get to the bank, but it really doesn't care if you actually have an account there. Compare that to the rigorous security posture we actually need in modern systems today. We need to be answering, who is this workload, what is their intent, and crucially, do they even have permission to access this specific HTTP method and path at this exact millisecond? That is a massive, gaping hole between basic location-based routing and actual robust security. Moving on to Section 2, Identity-Aware NBSR Architecture, shifting the paradigm from location to identity. So what exactly is Name-Based Secure Routing, or NBSR? Well, by definition, it's an identity-aware layer. It takes a logical service name, something like payments.internal, and instead of just handing you an IP address, it actually transforms that request into an authenticated, policy-authorized, and strictly temporary route. It literally forces identity and policy to act as the absolute gatekeepers before any network routing is even permitted to happen. If you aren't authenticated and authorized, you aren't getting a route, period. End of story. Let's move to and see how this builds, tracing the exact step-by-step lifecycle of a single request as it passes through the zero trust pipeline. First up, the workload client initiates a request, presenting its identity JWT and the logical service name. Second, the control plane intercepts this right away to validate that workload's identity. Third, it queries the Open Policy Agent, or OPA, which is operating on a super strict default deny authorization policy. Now, if OPA explicitly allows the request based on the identity, method, and path, we move to Step 4. The control plane issues a cryptographic ED2559 route ticket. Fifth, the client presents this shiny new ticket to the Envoy gateway. And finally, Envoy forwards it to the ticket verifier and the private payments backend. It's a completely airtight sequence where trust is continuously verified every single step of the way. Section 3. Anatomy of routing tickets, constraining access cryptographically. So the absolutely crucial point here is the strict, non-negotiable constraints applied to these routing tickets. We are not talking about generic access tokens. These things have an ultra-short lifespan of exactly 60 seconds. And why does that matter? Well, because the blast radius of a compromised ticket becomes incredibly small. But more importantly, they're cryptographically bound to the target service, cryptographically bound to the specific HTTP method, and bound to the exact request path. Meaning, if a ticket is issued for a GET request, there is no way you're using it for a POST. It's just not going to work. On top of that, it's validated against the intended audience and issued using dedicated, high-performance ED25519 keys. Section 4. Backend isolation and security, protecting the perimeter. Now, this is a real cornerstone of the architecture. The backend payment service is completely isolated on an internal protected network with absolutely no published host port, meaning clients cannot address the backend directly no matter what they try to pull. Only the control plane on port 8000 and the Envoy gateway on port 8080 are actually exposed. So if you try to bypass the gateway, there is literally nothing listening for your request. It is just a dead end. Beyond just network isolation, the system layers on some seriously robust architectural security. We're talking strict separation of ED2551 keys. You've got one set for the identity JWTs and a completely different set for the route tickets. It enforces explicit EDDSA allow lists and checks SPIFFE-like subjects and required claims. And if anything errors out, both OPA and the internal verifier strictly fail closed. Access is instantly denied. But the real kicker here is the fixed upstream mapping. The Envoy gateway ensures that the public API never, ever returns the backend's internal IP, so the client is left entirely blind to the internal topology. Section 5. Validated prototype results, empirical data, and prototype constraints. And this brilliantly illustrates the rigorous testing this prototype actually went through. Get this, 26 Python unit tests passed cleanly, alongside 5 dedicated OPA policy tests. But the real standout metric for me is that third line. 8 out of 8 mandatory security scenarios passed. The system successfully blocked every single attempted unauthorized access, path mismatch, and expired ticket they threw at it. And on top of all that, 15 Kubernetes infrastructure resources were successfully validated. Now, just to be fully transparent about how these tests were run, the Docker Compose environment was validated live during the hackathon. The Kubernetes manifests, those 15 resources we just mentioned, were validated offline. And this brings us to a critical distinction that the engineering team made very clear. This is a demonstration environment only. It is absolutely not production ready. The engineering team was actually highly candid about the prototype's limitations, which honestly proves a really deep understanding of the gap between a quick hackathon build and a true enterprise deployment. Right now, this prototype uses bare credentials, and it lacks a replay cache, rate limiting, and automated managed key rotation. For a true production evolution, all of those hardened, enterprise-grade features, along with high availability and a full SPIF or Spire public key infrastructure, would absolutely need to be implemented. Section 6. AI acceleration, human direction. The collaborative build process. Now, what's really interesting about this dynamic is how it perfectly defines modern software development. AI tools like GPT 5.6 and Codex were used heavily here, but strictly as accelerators to handle the raw code implementation, test generation, cross-platform scripts, and baseline security reviews. The humans, however, remained entirely in the driver's seat for the high-stakes decisions. It was the engineers who directed the core product concept, designed the zero-trust architecture, mandated the OPA default deny policy, enforced the cryptographic key separation, and deliberately scoped the project as a non-production prototype. The AI provided the raw speed for sure, but the human engineers provided the security and the boundaries. The code for this prototype is actually out there on GitHub for you to review, fork, and test yourself right now. And it's a project that really forces us to challenge our basic assumptions about network traffic. Think about it. If we're still routing traffic based purely on where a service lives, rather than proving who is asking and what they are explicitly allowed to do, are our networks truly secure at all? Something to chew on. Thanks so much for joining me for this explainer, and I'll catch you next time.